In this video, I want to talk about acid and base strength in organic chemistry. So what if we were to look at these two acids and ask, which one is a stronger acid? Well, what we would need to do is look at their respective conjugate bases. And then we would need to ask which one of these two acids create a more stable conjugate base. And I'll let you know right now, this fluoride is a more stable conjugate base than this carbon anion. So because this fluoride is a better conjugate, more stable conjugate base, we know this is a stronger acid than this. So, and again, it's a stronger acid because when it acts as an acid, it can afford to act as an acid because it creates a very stable conjugate base. So therefore, this readily acts as an acid because it creates a very stable conjugate base. But now you might wonder, why is this a more stable conjugate base than this carbon anion? Well, we know when these act as acids, we know they get these negative charges. They get these negative charges. And because fluorine is very electronegative, it likes that negative charge. It can deal with that negative charge, and so this is stable. Fluorine likes getting that negative charge, so that's why it's more stable. We know carbon is not electronegative. It's very low in electronegativity, so it hates dealing with that negative charge, so that's very unstable. So now we might compare these two acids and say which of these two acids is a stronger acid. Well, again, we need to look at their respective conjugate bases, and we need to see which one creates a more stable conjugate base. And I'll let you know right now, this iodide is a more stable conjugate base than this fluoride. So because this is a more stable conjugate base, we know this is a stronger acid, because it can more readily act as an acid and afford to act as an acid because it creates a very stable conjugate base. But why is this a more stable conjugate base than this fluoride? Well, iodine is actually less electronegative than fluorine, so there's more to it. So essentially what's going on is both of these ions have a formal charge of -1. However, because iodine is such a large atom, that -1 formal charge is spread out and delocalized over a large region. So we have a very low charge density, so we know that's stable. When we can delocalize negative charge over a large region, that's stable and that's energetically favorable. However, this fluorine also has a formal charge of -1, but this is a much smaller atom. So that formal charge is localized over a smaller region. So now we have this highly localized, high charge density, negative charge density region, which we know is unstable. So that explains why this is a stronger acid. It creates a more stable conjugate base because it's a larger atom, so therefore that negative charge is delocalized, which we know is stable. So one other thing I want to explain, so again, we said this was the strongest acid. And we said this one was the weakest acid. So that means this conjugate base is the weakest base. And this conjugate base is the strongest base. And we'll always see that theme, the stronger the acid, the weaker the conjugate base. And the way I like to think about this is, again, we said this was a very weak acid. Why was this a weak acid? Because when it acts as an acid, it creates this very unstable conjugate base, which is very unstable. So we know this hates acting as an acid. It hates losing its hydrogen because it creates this very unstable species. However, now that we know this is very unstable and we know it hates losing its hydrogen, so we know that means it really wants to gain a hydrogen. It really wants to go back to this more stable situation. So we know this hates losing its hydrogen, so we know it really wants to get a hydrogen. We know it's really desperate to get a hydrogen because this was so unstable. So because it's so desperate to get a hydrogen, that means it's a strong base. And that's the way I like to think about this and why weak acids create strong conjugate bases. So now another example I want to go over is let's compare these acids. Let's first compare this acid with this acid. Which is a stronger acid? Well, let's look at their conjugate bases and ask which is a more stable conjugate base. And I'll let you know right now, this is a more stable conjugate base. Why? Because there's resonance. They both have a formal charge of -1. However, this guy has that whole formal charge localized on this oxygen with that high charge density, which we know is unstable. However, this guy has resonance. We can see their resonance structures essentially delocalizing that negative charge. Instead of that negative charge localized with a high charge density on this oxygen, we can delocalize it over a larger region with the lower charge density, which we know is stable and energetically favorable. So this is a more stable conjugate base, so therefore this is the stronger acid. Now let's compare these two acids. Which is a stronger acid? Well, again, let's look at their conjugate bases. Which is a more stable conjugate base? And I'll let you know this is a more stable conjugate base, so therefore this is a stronger acid than this one. But why is this a more stable conjugate base? Because again, they both have that localized negative charge on the oxygen. However, this one also has these alkyl groups, and we know these alkyl groups are electron donating. We know they have those carbon-hydrogen bonds with these electron orbitals with negative charge electrons, so therefore they donate electron density. So this guy already has that localized negative charge due to this formal charge, but it also has these excess negative electron donating groups, making this even more negative with a higher charge density, which we know is unstable. This localized negative charge is unstable. So that's why this is less stable, and so this is a little more stable. So therefore, that's why this is a stronger acid than this one. And one last thing, now comparing this acid to this acid, just whenever we're comparing two, but one of them has one more extra proton and is positively charged, it's the stronger acid. So this one is a stronger acid than this one. And again, it relates to the conjugate bases. This is a more stable conjugate base because this has no formal charge. And this one does have a formal charge. So that's another theme. But again, and don't forget, just comparing these three, we know this was the strongest acid. And this was the weakest acid, comparing these three. So therefore, this is the weakest base, and this is the strongest base. So again, that same theme. So now let's see how hybridization affects the stability of acids. And again, I'm just going to focus on these two extremes, this sp3 carbon and this sp carbon, and this one would just fall in the middle, but I'm just going to focus on these two extremes. So which is a stronger acid? Well, again, let's look at their conjugate bases. Which one has a more stable conjugate base? And I'll let you know right now, this is a more stable conjugate base. So therefore, we know this is a stronger acid than this one. But why is this a more stable conjugate base than this one? Well, again, they both have these positively charged proton nucleuses. We know they both have these positively charged nuclei. And that's true with all atoms. But now this has this sp3 hybridized orbital with this negative charge due to these lone pairs of electrons. But this has an sp hybridized orbital with these negatively charged electrons. So now let's think about it. If we have these positively charged nuclei, we want this negatively charged orbital to be nearby. We want it to be snug and nearby so they can cancel each other out. So because this sp orbital is so snug, it kind of cancels this positively charged, and they cancel each other, destroying charge density. So therefore there's low charge density because they destroy each other. So that's stable. Where this one also has this negative charge, but because the sp3 orbital is a little further away, that negative charge isn't quite as close to this positive charge. So they can't cancel each other out as much. So that explains due to these orbitals. So therefore, we know this was the more stable conjugate base. So we know this was the stronger acid. This one is a stronger acid, and this is a weaker acid, and then this one would be in between. And again, we know this means this is a weak base, and this is a strong base. Because again, we know we always see those themes. So remember that. Remember that with these orbitals and how that affects the strengths. So now let's focus on bases. So let's compare this base with this base. Which is a stronger base? Well, to determine which is a stronger base, we need to look at their conjugate acids. And we need to see which one creates a more stable conjugate acid. And the one with the more stable conjugate acid is the stronger base. So I'll let you know this is the stronger base, and this is the weaker base. So therefore, we know this is a weak acid, this is a weak conjugate acid, and this is a strong conjugate acid. And again, we already explained that. We already explained how sp acids are stronger than sp3 acids. And again, it's the same idea. It's the same idea. It's just now we're looking at it in reverse. But again, it's that same theme. So that's how hybridization affects acid and base strength. So now let's compare these two bases. Which of these two bases is the stronger base? Well, we need to look at their conjugate acids and see which is a more stable conjugate acid. And I'll let you know right now, this is a more stable conjugate acid, so therefore this is a stronger base. This is a stronger base. So this is a stronger base because it creates a more stable conjugate acid. But why is this a more stable conjugate acid than this one? Because when they act as these bases, they get these positive charges. However, we know this one has these alkyl groups, and we explained alkyl groups donate negative charge density. So when this acts as a base, it gets stuck with this positive charge. However, it has these negative regions donating negative charge, destroying this positive charge. If we donate negative electron density, we destroy this positive charge. So now we have a lower charge. We have a lower charge density, which is stable. So that's why this is a more stable conjugate. This is a more stable product, essentially. So therefore, we know this is a stronger base. And so this was the weaker base. And again, another way I like to think about this is when comparing these two bases, we need to look at the lone pairs, because it's the lone pairs that steal the hydrogens and therefore allows these to act as bases. And really, you think which one has more electron density on these lone pairs? And the one with more electron density is the stronger base. So we know this was a stronger base, so therefore this one must have more electron density. And that's just something you need to get familiar with. If there's more electron density on the lone pair, then it's a stronger base. But why is there more electron density here than this one? Because, again, we have these electron donating groups. These electron donating groups are donating negative charge, creating a more localized negative region, so therefore it really wants to get rid of that localized negative region, and therefore it acts as a better base. So that's why this is a stronger base, because again, it has a more powerful lone pair of electrons. You can think of it that way, with more negative charge density. And now let's just compare these two. Just a rule of thumb, whenever we're comparing two similar bases, but one has a negative charge and therefore one less hydrogen, it's a stronger base. So this is a stronger base. This is a stronger base than this one, and this one's a weaker base. And again, it's related to, and then again, because again, this is a stronger base because it creates a more stable conjugate acid. Why is this a more stable conjugate acid than this one? Because there's no charge here. Here has localized positive charge, here has no charge, so that's more stable, so therefore that's why this is a stronger base. So now, another key point when thinking about acid-base strength is let's look at this guy, let's look at this guy, and let's look at these two nitrogens, and let's ask which of these nitrogens is more basic. And again, you could focus on the hybridization, you could focus on which one has more electron density and therefore a stronger lone pair of electrons. However, so let's imagine this one getting protonated. If this one gets protonated, it looks like this. And then we see, is this stable? Well, yeah, because look, we have resonance. We have resonance delocalizing this positive charge over a larger region, so we have a lower positive charge density, which is stable. So this one is a pretty strong base. How about this one? What happens if this one acts as a base? Well, if this one acts as a base and steals a hydrogen, we create this product. And is this stable? Well, not really, because there's no resonance. There's no possible resonance to stabilize this positive charge. And so this positive charge density is localized on this nitrogen, which is unstable. That high charge density, there's no way to go through resonance to delocalize that positive charge. So now we know this nitrogen is a stronger base. It's a stronger base because when it acts as a base, it has a more stable conjugate acid because, again, there's resonance stabilizing that positive charge. So now one last example I want to go over is this. So again, remember, resonance can have a big impact. Resonance can really stabilize the strength of a base. But now let's look at this guy and ask, is this nitrogen a strong base? Well, actually, no, because these lone pairs of electrons are participating in aromaticity. We have this aromatic system, so therefore, we don't want to destroy that aromaticity. This aromaticity is very stable, and if you haven't learned about aromaticity, don't worry about it. But the point is there's an aromatic system with these electrons, so therefore, if this acts as a base, we'll destroy that aromaticity. So therefore, this is a very weak base. It really isn't a base at all because it wouldn't destroy that aromaticity. Now the last one is let's look at this guy. Is this nitrogen a strong base? Well, no, because again, we need to think how much electron density is localized on these lone pairs of electrons, because again, we know if we have a lot of electron density, it's a strong base. However, these electrons are caught up in resonance. We have resonance, so we have these resonance structures. And with these resonance structures, we see that lone pair of electron is caught up in the resonance. So instead of these lone pairs being available to act as a base and to steal hydrogens, they're caught up in this resonance. And when we're in this resonance structure, now it can act as a base. So in fact, this isn't a base at all. We wouldn't consider this a base at all. This nitrogen, we wouldn't consider it a base. It's such a weak base because it's caught up in this resonance. So again, you need to keep in mind resonance when thinking about acid and base strength.